We've gone through quite a number of FPGA-based and system-on-chip-based hardware designs on this channel. For instance, the boards you see here, on the top left we could go anywhere from a simple AMD Xilinx Spartan 7-based FPGA, for example in this audio processing system. On the bottom left, we saw an FPGA-based hardware accelerator featuring an Arctic 7 FPGA that fits into a computer's M2 slot and uses PCI Express to communicate. On the right-hand side, we have two AMD Xilinx Zynq-based system-on-chip hardware designs featuring DDR3 memory, various regulators, interfaces such as Gigabit Ethernet, USB high-speed, and so on. I'll leave links to those videos and my courses in the description box below. The reason I'm making this video is that I've started a new hardware design featuring an AMD Xilinx Zynq Ultrascale Plus MP SoC. Now, these ICs are quite a bit more advanced than even the Zynq system-on-chips we just saw. While they are similar, they have many more features, and the hardware design for these ICs is much more involved. I'm currently just in the starting phase. I just about finished the first part of the schematic and did some basic PCB layout to get my sizing of the enclosure right and so on, and I'd like to go through this, at least this first stage, in this video. There will then be a follow-on video going through in detail more of the PCB design aspects, and then later, of course, testing board bring up as I did with the previous boards as well. The reason I ended up with this Zynq Ultrascale Plus system on chip is because it was available at the time, and it had very interesting features that I'd like to play around with, both from a hardware perspective, then also writing software, writing HDL for these parts. I'll leave a link to this in the description below, but they're rather powerful. They contain various different processors, they can interface with DDR4 memory, a lot of them will have PCI Express, and some of them even go to 100 gig Ethernet. They've got many cool features, and they are rather pricey. They come in different formats, so there's CG, EG, EV, depending on your needs. As we'll see later, I went for the EG line because this includes an ARM Mali graphics processing unit. If you're interested in more detail, I'd recommend looking through their website, but also going through their Zynq Ultrascale Plus MP SoC product table and product selection guide. Again, I'll leave this in the description below. You can see here what the use cases are for these devices. For this project, me personally, I just want to make a development board which lets us or me play around with various peripherals such as PCI Express, DisplayPort, and so on. But you can see here what this could possibly be used for, and these are very powerful processors and systems. They come in various different flavors. They start at about a couple €100, some 200, 300 euros, and go up into the thousands of euros, and they can get rather expensive. In comparison to the Zynq 7000 series, which we used in previous videos, these Zynq 7000 series are far cheaper, but then also quite a bit simpler as well. The actual system on chip I then ended up buying are these XCZU, so these are Zynq Ultrascale, and the variant is 2EG. The rest of these characters here denote the package, speed grade, and temperature grade. So SFVA65 is the package. It's a 625-pin BGA. The speed grade is 1, so it's the slowest speed grade, with an extended temperature range. You can see they are fairly pricey at about 317 euros a piece. There were two still in stock on mouse, and I bought them up, and I'll be shipping them to PCBWay to have them assembled when the time comes. Here, jumping over to Altium Designer, you can really see the starts of a PCB layout for this design. On the left-hand side in the Project Explorer, we can see we have quite a few schematic pages, and I'd like to run you through my overall thoughts when designing the schematic based around this system on chip, and in later videos, of course, we'll go into more of the PCB design aspects. A huge thank you to Altium for sponsoring this video. I'm using Altium Designer to design this board, as there are many different complex features. We'll have to route out DDR4 memory, various high-speed interfaces such as DisplayPort, PCI Express, and so on. And Altium Designer, as we'll see, contains many very useful features that aid me with this design. If you'd like to give Altium Designer a try for yourself, make sure to check out the link in the description below, or go to altium.com/YT/Phil's Lab, and you can get yourself an Altium Designer free trial, check out all the cool new Altium 365 features, as well as get 25% off your first license purchase. A huge thank you also to PCBWay for sponsoring this video. The PCBs you saw at the beginning of this video, all of these FPGA-based and system-on-chip-based PCBs, were manufactured and assembled by PCBWay. I will also have PCBWay manufacture and assemble this Ultrascale-based PCB, and this will be quite an advanced PCB, so I'll be using the advanced PCB service. Here you can go up to 60 layers, quantities down to a single PCB, HDI board with buried and blind vias, very small feature sizes, and any option you could pretty much think of when it comes to a PCB. So we'll see more of this when the PCB is manufactured and assembled. Make sure also to follow them on Instagram, and if you want, of course, you can also follow me on Instagram, where I post pictures of any new electronics that will be used in future videos. As you can see, the project is still in its very early stages, and keep this in mind while we're going through the schematic. There are things in the schematic that will probably still change, some things that might still be missing, and maybe some mistakes still in the schematic. Keep in mind I haven't checked the schematic yet, and this is just the first draft, which enabled me to do some rough placement and make sure this fits the enclosure that I've chosen, for example. As an overview of the components that are in this design, in the center we of course have our Zynq Ultrascale Plus, which is the 625-pin 0.8mm pitch BGA. I've added in a heatsink and some heatsink mounting, of course, because this does get rather toasty. In terms of peripherals, we have a whole power section, which I still have to put on the right-hand side. This normally runs off a 12-volt supply with a DC power jack, and we have quite a few different rails we need, as we'll see later. In terms of I/O, I've added in an SSD, which is via PCI Express in this M2 form factor, Gigabit Ethernet on the top left, DisplayPort, USB3 Superspeed, USB 2, and I've also added in a USB 2 hub to expand it to 4 ports. I've also added in an audio codec with line input, microphone input, as well as a headphone output. For further expandability, I've added in this FMC connector, which is an FPGA typical high pin count connector, just so we can expose quite a bit of I/O from the FPGA side of the system on chip. In terms of programming, we can either do this via JTAG, or I've added in this FTDI, USB-to-JTAG, and USB-to-UART circuitry with a USB connector. We also have 2 camera interfaces, these MIPI CSI, which go to the FPGA or Programmable Logic part of the system on chip. I've added in about 2 GB of DDR4 memory, some non-volatile flash memory, as well as 4 GB of eMMC memory. The last bit of non-volatile storage I've put in this SD card at the bottom here. Keep in mind the placement of all this might still change, but this hopefully gives a nice overview of what's on the design. Of course we have various configuration settings, some other peripherals as well, but this is the main overview. Pretty much just a straightforward development board, so let's go through the schematic. Before we get into the details of the schematic, of course we have to design our system from a system level point of view. So why do we even want to create the system? What specifications does the system have? What requirements does it have? And how do we choose the parts to meet those requirements? In my case, this is just a personal project, just so we can go through the hardware design in YouTube videos, and that we can explore different sections, for example, the DDR4 memory, PCI Express, and so on, and also the board bring up. So that's my reasoning, and that's why I want to make this board as generic as possible. However, for your situation, if you want to design for maybe a navigation control system or video processing system, of course your requirements will be different. For me, I just want to expose as much as possible. If you're new to this, and I won't be going to do much detail of part selection, as a guide to get you started, if you're new to these Zynq Ultrascales, is, for example, this Hardware Designer's Informal Guide to the Ultrascale Plus series, and I'll leave a link to this in the description below. And there are different parts to this guide, what, for example, different sections are of the Ultrascale, how to choose your device, and so on. For me, we already saw the device I chose. It was fairly cost-effective in comparison to the other Ultrascales, and it was available at the time, and had the interfaces that I wanted, for example, DisplayPort, DDR4 memory, PCI Express, and so forth. I've just created a blank schematic page here just to show you how large the symbol is and the schematic symbol is and how many different sections are within this Ultrascale. And this is a comparatively small Ultrascale, keep in mind. This can seem quite daunting, but if we break it down into several schematic sections and symbols and then create schematic pages for those sections, it becomes a fair bit easier. Of course, we have to power the device, and this is a 625-pin BGA. It's quite a power-hungry device, as we'll see later. We'll need many different switching regulators, many different rails. So the schematic symbol, of course, includes loads of ground pins, loads of power pins for different sections. As you can see here, there are so many different rails we have to connect this up to. Some of them can be consolidated, some not, as we'll see later. So we'll have all these power pins, and you'll immediately see at the top we have PS, which is the processing system. So this is the, for example, application processor part of this device. It's a system on chip, so it's split into PS and PL. PL is the programmable logic and pretty much the FPGA part of the device. These can be powered separately with different voltages depending on what you want to run your banks at and so on, but more of that later. So all of these power sections we have here, and then we have the first PS banks, and these are the I/O banks for the processing system. This is where we might hook up a USB physical layer or a Gigabit Ethernet physical layer, or we might connect UART, CAN, and so on. These are fairly flexible pins, but you still have to be concerned about the pin mapping, as I'll show you later. We also have another bank, I'll call this the configuration bank, where we have the fixed JTAG signals, we have various reset signals, mode signals depending on how we want to boot this device, if this is from an SD card, eMMC memory, and so on. We have a completely dedicated bank also to DDR memory. You can connect various types of DDR memory, for example, DDR3, DDR4, low power DDR4, and so on. And these are all these dedicated signals here. Depending on the device size, you can hook up, for example, 64-bit plus ECC wide data interbus. Many of these devices also include Gigabit Transceivers, and these are really useful if you want to use PCI Express, if you want to use, for example, DisplayPort or USB3 superspeed. And I do in this design as well, so this is why I also chose this part. Other than that, we also have the whole Programmable Logic section, and this is effectively the FPGA section. So we have these very many configurable banks and pins. These can run at different voltages and can have different functions. So overall, breaking it down, it does look quite complicated and there's many things you have to pay attention to, but there are distinct sections and banks that you can design around, and I'd like to guide you through how I did this for this particular design. For these fairly large projects, I of course like to do an overview page on my schematic, just indicating what systems we have on this design and where the connections are. Keep in mind also, again, this is a rough draft and I still want to clean up the schematic, do proper net coloring, net labeling, and cleaning up, for example, all these connections you see here. But this should hopefully give a good overview, a starting point. I'm about 3 to 4 weeks in of part-time work creating the schematic and creating the start of this design, and so maybe this is also a good indication of how long a project like this might take. On the overview page, we see we have power, the system-on-chip power pins, the processing system configuration, we have the FTDI-JTAG to UART USB, the whole processing system, which has various peripheral interfaces from the MIO, the MGT, which are the Gigabit Transceivers, which connect, for example, via PCI Express to the SSD, to DisplayPort, USB 3.0 superspeed, we have USB 2.0 high speed with the hub, some non-volatile memory, for example, the SD card, the QSBI flash, the eMMC memory. We have Gigabit Ethernet, the DDR interface, interfacing to memory ICs of DDR4 memory, as well as the Programmable Logic, which interfaces with the MIPI CSI cameras, with the audio codec. I still have to add in Wi-Fi, I'm not sure if I entirely want that, and of course the FMC connector. You might have also seen the MCU on the right-hand side, and this will also interface with some of the I2C devices, act as kind of supervisory role, and have control of the system fan, for example. The first page then is the power page, and as you can see here, there is quite a lot to this. We have the input voltage at 12 volts with some protection, as well as all of these different regulators. What you'll see on the top right-hand side is that I've also added in this power tree. Power tree meaning where my voltage sources, what are they being converted to, at what currents, and so on. My input voltage at 12 volts needs to be converted to all of these different voltages, and this is already consolidated, meaning typically you might even have more voltages and more power supplies required in your design. This information I took from the Zynq Ultrascale Plus datasheet, which is DS95, concerning the DC and AC switching characteristics. Here you can see the nominal and maximum minimum allowed voltage levels for all of these rails we saw in the schematic symbol overview. For example, you can see here we have 0.85 volts, we have 1.8 volts here, 1.2 volts here, and so on. So this is where you can get your nominal voltages at. Not only the voltages are of course important, but also the current draw and the maximum powers you can expect depending on what applications you run or what applications you implement. For this, and I'll leave a link to this in the description below, you can use the Ultrascale Plus Excel sheet where you can configure different loads and different settings, for example saying what core clocks your devices are running at, what interfaces you've selected at what different voltage standards, and this will then show you the power consumption per rail. And this is something you absolutely have to do to size your buck converters or your converters in general correctly. So this information from this spreadsheet combined with the Ultrascale Plus datasheet DS95 lets me draw up a very basic power tree. Keep in mind, you of course also have to add the current requirements and the rail requirements for any peripherals you have. So if I have an SSD, these can be quite power hungry at 3.3 volts, maybe a couple of amps, and I have to add that into this design. So that's why I did my power section last actually for this design. I added in all of my peripherals, then did my calculations, and then came up with this power tree. That allowed me then to choose all of these switching regulators and also linear regulators for the more sensitive rails, for example for the Gigabit transceivers. All of this information, again, via the datasheet, via this spreadsheet, and then of course choosing suitable parts as usual. You will have also spotted on the top right hand side, we have this power sequence here. We can't just turn on all of the voltage rails at once, we have to sequence them correctly. And again, going to DS95, we have a section on power supply sequencing, which tells you exactly what sequence needs to be done. The way I'm doing this is by having these enable and power good signals, and then so when one buck regulator's power good signal goes high, I use that to trigger an enable signal of a different power regulator. And this is how I then step through all of these various regulators, have my power tree and have my power sequence. And finally, that'll then initiate this power good signal, which then effectively triggers a reset of the ultrascale, as we'll see in a second. I won't go into detail of how I came up with the buck converter choices or these LDO choices. Please refer to the datasheets I just mentioned to help you do that. Then moving over to the second schematic page, we have the system on chip power, which includes the processing system and programmable logic. I've written down what voltage rails we need, just again as a reminder, but this of course is an interplay with the power sheet we just saw. We have all of these ground connections, which are simply hooked up to ground. We have the ADC connections via farad bead to the ground. And then we have all of these individual voltage rails, for example, the processing system at the top and the programmable logic at the bottom. You'll see a few different bypass or decoupling capacitors, some farad beads, and some different circuitry in place. And at the top, you'll notice I've added some notes or some screenshots which tell us how many and what type of capacitors we need per each of these voltage rails. Luckily for us, we don't have to come up with that ourselves. We simply have to go via the Ultrascale architecture PCB design. Now keep in mind, this is quite a generalization, and you should always do an analysis of your power distribution network before, during, and after layout to make sure you're achieving your PDN targets, but this is for a different video. I'd strongly suggest looking through this Ultrascale architecture PCB design guide, as this is not just for example, the power section, decoupling capacitors, but also for memory routing, I/O routing, and so on. And I'll leave a link to this in the description as usual. But going, for example, to page 10, looking at the decoupling capacitors, we can see, for example, for certain supplies, we need certain capacitors, certain farad beads, and they'll actually give you part choices as well. And that's exactly what I've transferred over here. Going further down, we can also see there's a section on power supply consolidation for these particular system on chips. And this is really useful because sometimes you don't need all of these different power rails if you don't want to turn them on and off individually. For example, here you might need up to 10 different power rails, but if you don't need to turn them on individually or you're not using certain parts, you can consolidate them and have less power rails that are required. And this guide also tells you about that. Again, the power section is something I did last, because this also depends on what peripherals you choose. In any case, let's go to page 3, which is the processing system configuration. This is bank 503, and I'm running that at 3.3 volts because my JTAG interface runs at 3.3 volts with my FTDI USB to UART and USB to JTAG converter. That's why I chose this to run at 3.3 volts. Now, while this circuitry might look slightly involved, why have I added all of these pull-up and pull-down resistors? Again, this is following the datasheets and application notes and user guides. I have my main JTAG interface, which splits off to a header, as well as to my FTDI chip, as well as to the FMC connector, in case I want to feed the JTAG on to a different device. I have various configuration signals, such as power on reset, system reset, done, init, program, errors, and so on. And these are either hooked up to LEDs to indicate some sort of status, or for example, the important signal, this power on reset signal, is triggered either by a user button or by the power good signal from the last buck converter that turns on, or the last regulator that turns on. Then we have these mode signals, so mode 0 to mode 3, and I've hooked them to pull down resistors, as well as I can pull them up via these dip switches. On the bottom left-hand side, I've extracted this from a user guide, and depending on the mode selection pin status, so if it's high or low, and what combination, you can boot from different devices, so from quad SPI flash, from USB, from eMMC, and so on. Then we have two clocks. One is the reference clock, which effectively clocks the entire rest of the system, and this is this 33.3 recurring megahertz crystal oscillator. You can run this at different frequencies as well, but the nominal standard is 33.3 recurring megahertz. We also have this RTC crystal oscillator for the real-time clock. What I can highly recommend when you're starting out with your own designs based on these fairly complicated systems is have a look at how other people have done it. And I've done that as well, of course, to make sure I'm heading in the right direction. Or, for example, for this peripheral circuitry, you can look at existing designs. And AMD Xilinx has quite a lot of them as well, but I also really like Digilent and their boards, and they have great schematics and great products in general that I highly recommend you check out. They have this Genesis ZU, which is a Zynq Ultrascale development board. Now, these are based on different parts than we're using, for example, in this design, but a lot of the external circuitry can be very, very similar. They also provide their schematics for reference, and this can give you some inspiration of how other people might have done it, how they've implemented the design, and maybe also help you out when you're deciding on your external and surrounding circuitry. I find this particularly helpful to double check if I've got the circuitry right here, for example, for this configuration section and so on. Effectively, this is boilerplate circuitry that we need there in any design, and you don't really want to reinvent the wheel. Now we're starting to get into the more interesting sections, at least in my eye. And these are the more configurable sections where you're not just simply following what needs to be done anyway, this boilerplate hardware, so to speak. This is the Zynq PS processing system MIO. And these are flexible IOs up to a certain extent. We have various different banks that can run off different voltages. And these will interface with I/O such as the SD cards, I2C, QSPI flash, Gigabit Ethernet, USB PHYs, and so on. As you can see, the schematic page isn't quite finished, but it's nearly there. The main interfaces are in place. The question is, how do you even come up with this pinout? Again, you could either just use a reference design, but my preferred method, and of course depends on what peripherals you need, is to go via the vendor tools. The vendor tool for AMD Xilinx is Vivado, and this is where I would create a new project, select my part, and then create a block design. In this block design, we can then place a Zynq Ultrascale by going to the add IP and typing in Zynq. Then we place in Zynq Ultrascale, and that's all you just need for this pin configuration. We double click on that, we get to this configuration panel. And this lets us see what peripherals we can use and how we can set them up and what pins there will be. So I could either, for example, click on one of these, for example, Gigabit Ethernet, and it jumps to this I/O configuration panel on the left-hand side. I've selected Gigabit Ethernet 1 for my design. If I expand this, I can see what pins those are on. So pin 38 is RGMII TX clock, and then we have all the data pins and so on. I can do this for PCI Express, for DisplayPort, selecting which lanes I want for my Gigabit transceivers. I can do this for my QSPI flash. I can do this for SD cards, UART, CAN, and so on. So that's how I would do this. This configuration I simply brought over to Altium Designer, and that's what you see here. Not quite finished, but the main things are in place. Then we have the processing system DDR memory interface in place. We can also, in certain cases, have a DDR memory interface for the programmable logic part, but here we have this fixed pinout, so to speak, for the processing system part. And we have our address command and control signals, our data signals, and depending on what memory you choose, DDR3, low power DDR3, low power DDR4, and so on, of course your naming will change a bit. But I'm using DDR4 memory. I have a 17-bit wide address bus plus 4 byte lanes for my data. And that then goes over straight to my DDR4 memory modules. I've added in two 1 GB DDR4 memory modules. That's why you can see that here they share a common address command and control signals. As you can see here, we have these two modules, but they have separate, of course, data byte lanes. So 2 byte lanes of data go to my first module, and the other 2 byte lanes go to my second module. They, of course, need to be powered with certain decoupling capacitors, again, taken from datasheets, and DDR4 memory runs normally at 1.2 volts, and that's also why this memory is powered off 1.2 volts, and of course the processing system bank for that memory as well. As we'll see in the future, in a future hardware design or PCB design video, I also have termination, and I'm routing this as a flyby system. So my address command and control signals start from the controller, go to the first memory module, to the second memory module, and for signal integrity reasons, I need to terminate that with an appropriate load, in this case, characteristic impedance of my traces. Again, fairly rushed in this video, but we'll see more of this in the PCB design video. Next, we have the processing system Gigabit Transceiver section. This consists of the MGT bank, which for this IC is bank 505. This has various sections. It has the transmit and receive, as well as clock input sections. You can see I've hooked up, for example, PCI Express, which communicates with the SSD, USB Super Speed, as well as DisplayPort. Again, going to Vivado, going to the I/O configuration and scrolling down, we can see we have PCI Express. I can choose how many lanes I want to use. I'm using 1 lane, and this automatically defaults to GT lane 0. And this is why I'm using lane 0 for my PCI Express. For USB 3 Super Speed, I'm using lane 1. And again, going to USB, I'm using USB 0 for the USB 2.0 high speed. But then for the USB 3.0, I need to use, of course, one of these Gigabit transceiver lanes. And I can choose my lane here. I've chosen lane 1. This is because I'm also using DisplayPort, and for this I'm using 2 lanes. I can either use the dual higher, which is lane 2 and 3, or dual lower, which is 0 and 1, but then of course we get a conflict, and that's why I use dual higher. And that's why I have this configured like so. I also need reference clocks for each of these transceiver sections, so this depends on what protocol and what interface you're using. To figure out what clocks you need, I'd recommend looking at the technical reference manual for the Zynq Ultrascale Plus, and that's user guide 1085, and going to the reference clock network section, which is part of the PSGTR transceivers. Here we'll see that for PCI Express V2, we need a 100 MHz reference clock. For USB 3, we can use either 26, 52, or 100 MHz, and for DisplayPort, one of these frequencies. And that's what I'm feeding into this bank using this IC. This particular IC is a fairly dynamic clock generator. It has 4 outputs, which can feed these clock inputs. I'm also using the 4th output to actually generate the clock for the SSD because the MGT itself cannot do this. These are only clocking inputs. There's of course some boilerplate hardware, some supporting circuitry around this, some decoupling capacitors, pull downs and pull ups, but effectively this is an I2C programmable clock generator which requires a single clock input and can generate all of these different clocking frequencies when we program it via I2C. So this is connected, for example, to the processing system I2C. So very easy to do and a fairly simple interface. Connecting to the MGT transceivers, we have, for example, the SSD, and quite simply, I've just put in an M2 key M slot, hooked up the PCI Express, various GPIO that's required for this implementation, and of course power, and this runs off nominally 3.3 volts. So nothing too complex here. To get the pin out for the M2 key M connector and know which key I need to use, I went by this application note by Codec, and they have the key M pin out description, as well as a reference design for the various connections you need. And this is then just this M2 SSD we see over here in this 22 by 80mm form factor. Other than the SSD connecting to our MGT, we also have USB 3.0 super speed in addition to a USB 2.0 high speed via a physical layer. So the actual super speed connector is on the right side here, which is this USB 3 micro B connector, and that simply connects pretty much point to point with my MGT. For the TX lines, I do need some series AC coupling capacitors at about 100 nanofarad to 200 nanofarad in series, and those are only on the TX line. So fairly straightforward connections, but for the USB 2.0, this is coming from the processing system as we saw before. We have this ULPI connection, and that needs a physical layer to effectively translate this to this USB 2.0 high-speed differential pair, which goes to the connector. For DisplayPort, which is our last MGT connection, fairly straightforward connections as well. The differential pairs come from the MGT, AC coupled with these 100 nanofarad capacitors, pretty much straight to and from the connector. Powered via 3.3 volts. We also have these various configuration signals as well as the auxiliary channel for configuration. And this is going through this rather interesting network at the bottom here and converting these to these single-ended individual signals. This information I took from an AMD Xilinx development board, and this is the ZCU102, which are freely available after registering. And the relevant schematic symbols and parts are shown here. This is effectively what I took over for my own design here. There's no need to reinvent the wheel. Take what works and implement that for your design. That's what these reference designs are for. The Ultrascale Plus is capable of running bare metal code, in addition, of course, to the HDL, but of course it can also run, for example, Peta Linux, which is an embedded flavor of Linux. To do so, we need some additional non-volatile memory. The most basic type for these types of devices is QSPI flash memory, the rather simple interface for bidirectional data lanes, clock and chip select, but I've also added in an SD card, which makes it very easy to load on Peta Linux, as well as some eMMC memory. All these connections are very straightforward, pretty much point-to-point connections, the usual bypassing and decoupling, and the pinout, of course, from Vivado as before. We do have to be a bit careful though of what configuration memory or what non-volatile memory we choose, as not all memory types or not all memory is supported. To find out what is supported, we go to User Guide 908, UG908, look at the Zynq Ultrascale Plus configuration memory devices, and you can see the type, for example, eMMC, NAND, QSPI, and so on. In particular for the QSPI memory, you have to choose the right vendor and right part, and that's what I've done for this schematic as well. In terms of programming, at the start of the video, we saw that we can either use the JTAG header, or we use a USB-to-JTAG and USB-to-UART converter in the form of this FTDI chip right in the center here. The schematic is fairly straightforward. We have the FTDI chip, we have some EEPROM so we can configure the device at boot, some clocking, decoupling, our USB connector with some ESD protection. On the other side, we connect to the Zynq's JTAG, as well as to the processing system UART, and this is something I definitely recommend you do, is expose at least one UART for a debug interface. The schematic, you can either come up with yourself or again go to User Guide 908. At the time of making this video, you can now reprogram FTDI devices without requiring a paid-for license, which means you don't need an external dongle or so on. And it supports these following FTDI devices, and nicely enough, they also give us the schematics, which I took pretty much directly from this VCK190 schematics, which are available here. Here we have a slightly unfinished page. This is the Programmable Logic, so not looking at the processing system. We have various different banks, so bank 26, 64, 65, and 66, and they all serve different purposes. Bank 26, I'm running off 3.3 volts because this then interfaces with the codec via I2S, and also the eMMC memory, I'm actually using these pins, as we'll see on a later video, which are then routed through the programmable logic section to the processing system. And this is what's known as EMIO, Extended I/O. I'm also going to attach some more LEDs here. Right now, I just have an RGB LED. For bank 64 and 65, they are interfacing with this FMC connector, so effectively just generic interfaces, loads of differential pairs. And bank 66 is running at 1.2 volts, which is required for the MIPI CSI interfaces, so for my cameras. The cameras are quite straightforward, effectively just point-to-point connections with some ESD protection, powered off 3.3 volts, but the signaling is at 1.2 volts. We also have these power-up signals to turn on and off these cameras, and these go via level shifter to the programmable logic bank, also running off 1.2 volts, and that's why I need this level shifter. But there isn't very much to this page, very simple point-to-point connections. We also, of course, have the audio codec connecting to the programmable logic. This just has I2S and I2C, various filtering and decoupling, and then we have our line in, line out, and phones. And this is using a MAX 9867 codec. Very simple to use, very simple to interface with, and that's why I chose it, and fairly inexpensive. We don't have particular hi-fi requirements for this design, so something cheap, very simple to implement with surrounding circuitry is what I went for. Other than that, the remaining few peripherals we have Gigabit Ethernet, where we're using a Gigabit Ethernet physical layer. This is connecting to the processing system as we saw before. Again, very similar point-to-point connections, bypassing decoupling, and then going to an RJ45 connector with integrated magnetics. This particular physical layer I actually used before on a previous design using an AMD Xilinx Zynq system on chip, so a far simpler IC, and this is a natively supported physical layer. This is an RTL8211 by Realtek. And I'd suggest using parts that have been verified on previous dev boards on previous hardware designed around your specific system on chip or IC that you're choosing. This is quite nice because then I could reuse my schematic for this particular IC and be pretty certain that that'll work. Finally, I have USB 2.0 high speed and a USB 4 port hub. For my high speed, I'm just using the connections coming from the Zynq PS, which is ULPI, feeding to a physical layer. Again, choose a physical layer that has been proven to work with the particular system on chip you're using. And this particular USB 3320 has been proven to work. Very simple to integrate with, doesn't require a lot of external circuitry, and simply has a USB differential pair, which I can then feed into my USB 4x hub. This is again very simple to set up with, just needs a clocking source, various strapping options to put it in a certain mode, which you can all get from the datasheet and reference designs. This then goes into 4 USB-A connectors, female USB-A connectors with some ESD protection, and load switches, which are controlled by the USB hub as well, with these power enable and overcurrent flag detect pins. These digital designs, a lot of them are fairly straightforward. It's more of a system level design and then working out the details from the datasheets, reference designs, and application notes, and then putting all these pieces together. So that was a very quick walkthrough and overview of the schematic design based around an AMD Xilinx Zynq Ultrascale Plus device. There's quite a bit to this, but if you break it down, work section by section, look at datasheets, application notes, and put the pieces together, it actually ends up being straightforward, although it's quite a lot of work. For me, at least the most interesting part of this is then actually the PCB design, and this will also be interesting in terms of a board bring-up perspective and so on. If you have any other ideas of what you'd like me to add to this development board, please let me know down below in the comments. I do plan on making this board open source once I've created the final hardware design, had it manufactured and assembled and tested. Thank you very much for watching this video. I hope it was useful and it gave you some insights on what to consider when you're designing based around an AMD Xilinx Ultrascale part. We'll go into more detail as I progress through this hardware design, especially when it comes to the PCB design aspect, again to me the most interesting, so make sure to subscribe to stay up to date with any future videos. Thanks again for watching, and I hope to see you in the next one. Bye bye.